so we can start. Okay, so thanks, Gerard. Okay, so welcome, everybody, and good evening, right, to our members in Denmark and the others in Europe. And maybe I have to say maybe good afternoon and good morning, right, to others. So welcome to the IEEE Region 8 Virtual Student and Young Professionals Congress 2020. So today hosted by the Denmark section. So yeah, so this is the program today. Okay, so we are a bit late, but I hope we can manage it. So yeah, it should be no problem. So first, Johan and I will give a welcome message here. So I'm Wei Zi, and now is the chair of the IEEE Young Professional in Denmark, and Johan is the chair of IEEE Denmark section. And then we have a technical talk on the challenges and issues in integration of the renewable energy sources. Our keynote speaker is Professor Sukumar Mishra. And later we have a panel discussion on a similar topic on the renewable energy sources. So we have a panel member. So of course I will introduce later, but basically is our keynote speaker and our EXCO are the members of the IEEE Young Professional in Denmark. So, okay, and here I'd like to play a short video supported by our Copenhagen Conventional Bureau to welcome back to Copenhagen. Okay, so yeah, I hope that we have a chance, right, to meet in Copenhagen in near future. And then I'd like to briefly introduce our Denmark IEEE, the young professional. And actually, we were initialized in July last year. So we are young, but we have been active in many events. So we also support the IEEE the connecting experts events. So we have the speaker there, Jan Kastrup, and talking about the threat landscape under the COVID-19 situation. And we also collaborative with some conferences and workshops, right, on the cybersecurity and IoT security to provide the chance for our members in Denmark to learn the information from both the academia and industry. And we also today we have the IEEE the R8 the virtual student and the young professional event here. And this is the current organization team, right, from us. So we have Rui as the vice chair here, and we also have Sabahan as our secretary. But right now we are still looking for a chair here, right? So if anyone from you in Denmark, if you have an interest, right, feel free to contact us. Okay, and then let's welcome Johan to give us a welcome message. Johan.
Yeah, thank you, Wei Zi, for organizing all those stuff over here. And good evening, everyone, if you are based in Europe, and good morning, good afternoon, if you are from somewhere else. So we know that due to the COVID-19 stuff, then we can't travel, and we use these high-tech technologies to do virtual events. And this is one of the events and the IEEE is trying to bring to its members. But of course, this IEEE Reading Aid, Students and the Young Professional Congress, I think it is a very old event, but this year it's very special. And as I mentioned, it is a virtual one. And of course, thanks to the efforts by the IEEE Young Professional Affinity group in Denmark, with Ray and also Sukham, they have put the effort into this one and make this program. So I'm very looking forward to the technical talk by Professor Sukumar Mishra from IIT Delhi. And then also I'm very looking forward to the discussions on the some technical measures for integrating renewable energy sources in the future power grid and in the power system right now we have. So once again, thank you all for joining us for this special event. And I will be very happy to talk to you all later through the program. Thank you.
Thanks very much, Johan. So then let's move to the technical talk. We'll also let's welcome Sukumar here. So the topics, the challenges and issues in integration of the renewable energy sources. So Sukumar, yeah. So I will hand it to you.
Yeah.
So you can introduce. Yeah.
Yes. Thank you, VZ, and welcome, Professor Sukumar Mishra. So I would like to introduce him before starting the technical talk. So Professor Mishra is a professor in Indian Institute of Technology, Delhi for the past 17 years. He has won many accolades through his academic tenure of 27 years. He has been a recipient of Young Scientist Award by Orissa Bigyan Academy, INSA Medal for Young Scientist, IEEE Young Engineer Award, IEEE Silver Jubilee Young Engineer Award, Samanta Chandrasekhar Award, Bimal Bose Award, and Nasi Reliance Platinum Jubilee Award. He has recently been selected as Mission Innovation National Champion in the year 2019 under the Mission Innovation Initiative to accelerate clean energy in India. He has been granted fellowships from academies like National Academy of Science India, Indian National Academy of Engineering, and professional societies like the IET in UK, IETE India, IE India. He has also been recognized as the INA Industry Academic Distinguished Professor. Apart from all research and academic collaborations, he's very actively involved in industrial collaborations. He's currently acting as the ABB Chair Professor and has previously delegated as NTPC, INA, and Power Grid Chair Professor. He has also served as an independent director of the Cross-Border Transmission Company Limited and River Engineering Private Limited. He has also carried out many industrial consultations with Tata Power, Microtech, and others. He's a great enthusiast of innovation and has supported many startups in the past, and recently has incorporated a new company called Silo Solutions Private Limited under the Companies Act. This company deals in products related to renewable energy sources utilizable at household scale as well as at commercial setups. For example, bidirectional EV supply equipments, AC EV charging, DC EV charging facilities, grid-connected solar inverters, and smart management in homes. Professor Mishra's research expertise lies in the field of power systems, power quality studies, renewable energy, and smart grid. He has also been functioning as Associate R&D of IIT Delhi that's in India from March 2020. He has so far authored more than 70 IEEE transactions and journals, 30 IIT journals, and 30 other international journal papers. He has supervised, he's currently supervising, he has supervised 31 PhD students, 18 ongoing, and 38 master students, 2 ongoing. He has also co-authored, authored and co-authored 5 book chapters so far and has 13 patents to his credits. He has been working in close association with the IEEE Delhi Section Executive for the past few years and is currently serving as an editor for many IEEE transactions. So with that, on that note, I would like to welcome Professor Sukumar Mishra, and please go ahead with your presentation.
Thank you, Shubham. Now I'm just trying to share my screen. Are you able to see my screen?
Yes, we can probably go in the full screen mode.
It's
Yes.
visible?
Yes, it's
Okay. So good evening to all of you, and good morning as well as good night, and many other accolades coming in the time zone. So we are basically in a time, temporal, and spatial system. So thanks to COVID, that it has made us a temporal and spatial domain creatures. With these basic notes, if we see, the renewable energy is also coming in different time frame in a day. And as we see, the photovoltaics also varies with respect to time in a day. Specifically, in the morning, its power output is low, and in the evening, its power output is low, and in the noontime, it increases. So this time variation creates a temporal effect in the photovoltaic system, as well as in the geographical domain. When the photovoltaic system are distributed, it gives rise to a spatial domain behavior. So, as a nutshell, the renewable energy and specifically the photovoltaic behaves in a temporal and spatial domain. Now, since it behaves in a time and spatial domain, it is intermittent in nature and uncertain in nature also. When the time zone or the time variation is large, we categorize them to be intermittent, and when it is not able to be determined, we call it as a uncertain behavior. So this behavior of intermittency and uncertainty taken together makes the photovoltaic energy as a source quite challenging. This is because we all know that the generation and the load must balance each other. If it is not balancing, then we need a storage. Now, when we talk about storage, it becomes costly because we have to go for some sort of storage element like maybe battery or maybe many other storage sources like the compressed air, like your geo energy store system, like your hydrogen storage system. In all these storage systems, the most popular one is the battery energy storage system. Now, this battery energy storage system, when you want to put with a solar photovoltaic system, then the cost become very, very high. As a result, people thought that initially, can we do something so that the battery energy storage system initially may be sacrificed. We may not use battery initial stage. When they think about this, they come to the answer that yes, we can use the grid as a storage, because the grid is a passive device, no doubt, but it is such spatially distributed that the energy entering from one end will reach to the other load end. With this basic introduction, if we go to the renewable energy integration to the grid, then yes, we get a benefit of cost, but we enter into some challenges. Now, to understand the challenges, we must first understand what is the grid-connected photovoltaic system. You can see here, a grid-connected photovoltaic system will have a photovoltaic panel that can be now interfaced with a DC-DC converter to take the voltage to a desired level, and then an inverter can be connected to supply the power to the grid. Now these two, because there are two stages, we call this type of schematic to be double stage grid connected schematic. On the other hand, we can make it also single stage grid connected schematic by going for many photovoltaic panels in series and reaching to a desired voltage level so that the inverter can work. Now, based on the country's regulation, you can have a transformer at the interface point of the inverter and the grid, or you may not have a transformer at the interface point between the inverter and the grid. It depends on the law of the country. Now, if we go for that, then if you have a rooftop solar photovoltaic system, that rooftop solar photovoltaic system will be connected to your DB point in your house, and that DB point will be now acting as the grid, and that house can also have certain loads. So the photovoltaic power will be an interface between the grid and the load. Hence, when the load is higher than the PV power, power will come from the grid. And when the load is less than the PV power, power will be going to the grid. So this consumer, this house, which was a consumer earlier without photovoltaic, can now become a consumer at certain time and can become a producer at certain time with respect to the grid. So because now the same entity acts as consumer as well as producer, we give this entity a new name called prosumer. A producer as well as a consumer combining together, we call this to be a prosumer. So when this consumer become a prosumer, and when it will produce or when it will consume become more uncertain. So you can see here that PV is intermittent and uncertain. Now your load is intermittent and uncertain. The probability of this uncertainty may be linked or may be delinked. They may be independent event or they may be dependent event. And because of this complex system, the grid will see this prosumer a very, very uncertain entity, and it do not know when it will be a producer or when it will be a consumer. So to overcome this to some extent, we go for forecasting in the system, but still, though it can reduce to some extent the uncertainty, but still a large quantity of uncertainty remains unanswered. Now, if we go for that operation of prosumer, then the grid need to be connected to the inverter. And when we want to connect this grid to the inverter, then I will need to go for a synchronization procedure. So when I go for this synchronization, the waveform of the two entity need to be same. That means it will have the magnitude, frequency, and phase angle that need to be same. This is very easy when you have a rotating machines getting synchronized with the grid, what we know. But when we go for a inverter getting synchronized with the grid, generally we go for a PLL, which is nothing but a phase lock loop. And this PLL now try to produce the grid voltage waveform, and with respect to that waveform, we will go for our reference command, and that reference command will be now used to synchronize the inverter to the grid. This makes a system little bit more tricky for the Indian conditions. In India, many a times the grid fails. No doubt in the urban area, we have stabilized it to a large extent, but in the rural area, still the grid is intermittent. Now, when it becomes intermittent, the photovoltaic system, even if grid connected, cannot produce the power because there is no reference signal coming to the photovoltaic. Therefore, at many big industrial entity or hospitals and some other business platform, we go for a diesel generator set, which need to be operated in parallel with the photovoltaic to produce the reference signal from the diesel generator, and the photovoltaic system get synchronized with the diesel generator. This gives us a benefit of diesel consumption, and in the long run, it becomes very, very, very cost effective. So the grid connected photovoltaic system, in the real sense of grid, becomes now a virtual grid connected photovoltaic system, where the diesel generator acts as a virtual grid. Now, since we are getting the waveform through a PLL, and the PLL is nothing but a transfer function in NOT cell, it is having the PI controller and filters included into it. As a result, the PLL will have its own dynamics. And this dynamics, when integrated with the dynamic of the grid, it plays very, very vital phenomenon in the inverter-based thing. And that inverter, which is now referred or which is now getting reference signal from the PLL, will be in unstable mode of operation when the grid voltage will have power quality issue. That means the voltage of the grid is not absolutely sinusoid, but it is having distortion imbibed into it. Therefore, the PLL dynamics in a grid-connected photovoltaic system need to be properly looked into, and the dynamics integrated with the grid behavior is a study or is a research topic that need to be seen in depth. Now, because you have the grid-connected system, we want to extract the maximum power as much as possible. Therefore, we go for the maximum power point tracking of the photovoltaic system, and we try to operate at the maximum point here. Now, this maximum point operation is called as MPPT, that is maximum power point tracking operation. However, under many circumstances, we may require to control the power output from a photovoltaic system. They are just like in our synchronous machine, we can operate at any point. Like that, we want to operate this. So we cannot go beyond the MPPT point, but we can always reduce the power out. So this operation is called as derated mode of operation, or a dispatchable mode of operation, or a power output based operation. So many names exist, and where basically the photovoltaic system will be operated through a power command, not by the MPPT. However, the power command will have a upper saturation point, which is nothing but the MPPT point. So when we do this derated mode of operation, now this can be done to achieve certain grid advantage as well, which we'll discuss later on. So this derated mode or off MPPT PV operation in a grid connected mode of operation may be required to go for ancillary services like frequency response and voltage response coming from the grid connected inverters. So the grid connected inverter, because as I have already mentioned to you, is having a PLL, then now the question becomes whether I will control the current or I will control the voltage. Because it is a grid connected system, I cannot change the voltage of the grid. So I modify the inverter to be acting in the current control mode of operation. So if we go for the current control mode of operation, then I will inject certain amount of current into the system, keeping the grid voltage intact. Under that circumstance, I am in fact injecting a given power into the system, and the inverter becomes a PQ mode of operation. I inject certain amount of P and I inject certain amount of Q. Now, if I relate this P to MPPT, then I am not having any control over P, but I can only have the control over Q. But if I do not link it to MPPT, I can control both P and Q. P is in a limited sense, and Q is according to the capacity of the inverter. So when I do that, that control can make the photovoltaic system a dispatchable source, and that can be achieved using a derated philosophy. And when I do that, I will end up in a real and reactive power injection into the system. That means I can go for a set point operation of real and reactive power, where I can command the inverter with the desired amount of power, with the constraint that the real power need to be less than the MPPT power, whereas the reactive power will be within the capacity of the inverter. When I conclude that the power will be real and reactive power, and that is to be achieved with current injection, so the in-phase component is decided and the reactive component, that is 90-degree component, is decided. The in-phase component decision can be done by many approach. One of the approach is VDC ref minus VDC. And if this DC voltage reference is obtained from MPPT algorithm, then this IP will track to MPPT, and this reactive power can be obtained through a droop mode operation with respect to the voltage, or a PI mode operation with respect to the voltage. Generally, this PI mode operation is not followed because ultimately this reactive power will hit to the upper limit at many a times. So droop mode is generally considered, but yes, in some cases we can go for this if the photovoltaic system is a park, like you can assume that it is a 300 or 400 megawatt solar park having higher capacity of inverters. So when we go for this photovoltaic and we integrate that into the grid, the impact of photovoltaic can have manifold. So the impact on distribution system is there in both steady as well as dynamic in nature. So the change in network voltage profile, which includes voltage rise and unbalance, will be one of the impact of photovoltaic integration into the grid. Similarly, the feeder loading, including potential equipment and component overload, can be another impact of the photovoltaic integration. Besides, you can have the inertia of the system reduced by a large magnitude, and this becomes specifically significant for weak system. Overall, and not the least, you can see the operation of OLTC, that is online tape changer, and line voltage regulator, as well as capacitor bank, that is switched capacitor bank operation, becomes more frequent when the photovoltaic system is integrated. So this is the challenge when we go for the integration of PV into the AC grid, how to handle these issues. Besides that, some more challenges could be the power quality, the PV intermittency lead to voltage fluctuation, and the power quality, if the inverter is not proper, then it can have your harmonic injection into the system. Similarly, the overcurrent and overvoltage protection can also maloperate, and the overcurrent protection equipment will be need to be properly designed, and the setting point has to be properly made so that the integration of photovoltaic will be sustainable in nature. There may be some changes in the electric losses, that is power losses, and reverse power flow may increase also the loss. Similarly, the variation of power factor is a very important factor which is seen when you go for photovoltaic integration into the grid. You can see here a representative nature to give a overview of the reverse power flow phenomenon. You can see here that at 0% loading, that means the photovoltaic integrated system, when there is no photovoltaic integration, this blue line is the power flow that is happening in the feeder. Now, when you go on increasing the PV integration, then after certain time, you can see here that it goes to negative. So when the integration becomes around 40%, it goes to negative in some of the time of the day. This says that if the PV penetration is higher, you will end up in a reverse power flow. And that will go on increasing further and further. And the neck of the duct will become very large, and you need a large ramping of the power when you go for a larger penetration of photovoltaic power into the grid, and that also will increase the large amount of reverse power. Similar scenario will also occur when you go for the voltage rise phenomenon. Generally speaking, the voltage in a feeder, when there is no photovoltaic or no DG integrated into the system, will go on falling when you go towards the last mile from the substation. So to increase this profile or to make the profile better, we go for capacitor placement. And when we put capacitor placement, it becomes more or less flat. However, when you go for photovoltaic integration, the PV system makes the thing, the voltage, such that the voltage will go on increasing, and it should go on increasing. However, after this point, if the photovoltaic injection does not have any the houses do not have any photovoltaic on their rooftops, then the voltage remain more or less flat. So this says that the voltages at certain point on the distribution system, node voltages, may see a voltage rise phenomenon, and that voltage rise may be coupled with voltage fluctuation when the photovoltaic power become intermittent, and that could be due to some cloud movement in the system. To handle this voltage rise, generally we go for the capacitor bank and OLTC operation, and these OLTC operation, being mechanical in nature, creates lot of problem in the grid connected mode of operation. Another interesting phenomenon happens, which says that when you increase the photovoltaic penetration, the loss in the system will increase. When the loss in the system increases, the cables which is actually taking the power now become more heated up, hence the failure rate will increase. And that says here from the graph, you can see here that after certain injection, the loss, instead of reducing, it increases, and it becomes much higher than what was happening earlier without photovoltaic integration. So this increase in loss makes many a time a grid integrated system not to operate at its fullest capacity, but to forcibly derate the integrated system such that loss is within control and my cable do not get overheated up. Besides that, when the photovoltaic penetration becomes more and more, the inertia of the grid becomes less and less, and hence the net inertia, effective inertia of this system reduces. Hence, we must do something with the integrated system at least, photovoltaic integrated system at least, so that it produces virtual inertia. So to get to the virtual inertia, we produce the real part of the component from the change in frequency, and first derivative, second derivative thing can be added here, such that this real power component of current will be proportional to that, and I can get virtual inertial response. Nevertheless, the grid connected system has to be seen with respect to the power quality issue, and the power quality issue may be your voltage unbalancing, current unbalancing, and harmonics injected into the system. All these things can also be handled by the same inverter by modifying the reference command, that is reference current command, going into the inverter, because many of these power qualities issues can be handled by injecting the reactive power component only into the grid in a proper way. And by injecting reactive power, I am not going to hamper in any way the real power produced from the photovoltaic system, and hence I can make a multifunctional inverter which can regulate many of the grid connected issues. Thank you for giving me a patience hearing by listening to this grid connected issues and its implication in the photovoltaic sense.
Thank you so much, Professor Mishra. It was a very interesting and pedagogical presentation and I'm sure it will help the young professionals take up these research challenges in the future and strive to aim for a greener future grid. I know that it's quite late, so thank you so much for joining in. And now, as per our agenda, we will move forward to the panel discussion. I would also like to involve Rui and Yongheng, where we can discuss about the challenges in integrating or having 100% renewable energy grid, as that is the global objective right now, as we know. And what can be the measures and what are the challenges first, and what can be the measures which can be used to take care of that. So I will start with that. And in the meantime, if anyone has any questions, Gerard, how are we going about that?
Yes, thanks so much for the keynote.
Yeah, so
actually,
we will have in the
Gerard,
chat. So I think
some questions. So basically, I think Gerard can post the questions right to the
yes.
Zoom chat. So all the panel members they can read the question. So it's easier for us. Yeah. Then we can start the panel session. Yeah, the panel discussion.
Yes.
So yeah, as you all know that because Denmark focus put a lot of resources on the energy part. So it's very, very important, right, to Denmark. So,
yes.
Okay, yeah.
There is a question I am coming in the chat, that to what extent does the PV inverter create losses, if any, as the PV system is scaled off? I have already shown a graph, a rough estimate graph, that the base load of the system, that is your distribution system, for a distributed distribution transformer is approximately 30 to 40% of its peak load. So if my connection is X kilowatt or something like X megawatt. It depends on the distribution area, and it is around 30%. So when my photovoltaic system exceeds that base load, then there is a possibility that I will end up in a reverse power flow. So if the base load is around 30 to 40%, then the cancellation occurs at that. And now if I go for 100% penetration sort of thing, that means if my DT is 1 megawatt and the base load is around 300 kilowatt, and I am going for a 1 megawatt photovoltaic injection, that is 100% injection, then my reverse power flow will be around 70%. So for 30%, if I am getting X amount of loss, for 70%, it will be square times, because the loss is proportional to I square, and it becomes very, very high. Therefore, we have to be very, very careful in integrating these photovoltaic system. And in Indian condition, we generally put a cap of around 50% around. We don't allow beyond that to go in a grid connected mode of operation.
Yes. So yes, we will have more questions. In the meantime, maybe we can start with what can be the challenges when we strive towards 100% renewable energy sources based future grid. So Yongheng, we can we can start with your opinion first, and then we can also ask for Professor Mishra's opinion. So maybe you can start.
Yeah, thank you, Subhan, for the coordinating this one over here. Yes, and yeah, we see that actually, of course, seeing from the Danish government policy, and the government is trying to reduce CO2 emissions, and one of the ways, of course, that we put more renewable energy into the electrical generation. But of course, the other thing is also it creates many challenging issues, as Professor has presented in a technical talk. So I would say one of the things when we look at the current structure of the entire electricity grid, and in the long term, it will be still a mixed power grid consisting of various renewable energies that are power electronics based. And but in the future, we don't know, but I would expect that the penetration will be much more higher than in that sense. The challenging issues we see today, like the inertia issues, like the control issues, dynamics issues of the systems, may be different. But in that way, and we may come up with some novel solutions to take care of the entire power systems. And yeah, I would say when we're looking at when we look at the future, and for 100% renewable generations, probably at that moment we don't have to worry about the control issues by then, because the system is purely power electronics based, and then that can be of much high controllability in that way.
Yes. So do you think, let's say, the more number of grid forming converters can also lead to, well, other issues such as maybe power system restoration? Because as we were discussing a few days ago, that there was a blackout recently in Sri Lanka. And as they have reported that the power system restoration took actually 8 hours to be back, or, to restore some of the loads, because the renewable energy sources were basically not allowing the the synchronization process. So do you think these kind of problems may happen in case of some critical events such as blackouts, or which is quite common these days?
Yeah, I would say when you are talking about referring to the blackout recently happened in Sri Lanka, but there's another case, another example that was last year's in the UK. Then the power grid failures because of large scale penetration of renewable energy systems. But of course, when we look at the current grid structure, because we have a conventional synchronous generators, that's sort of the system that has physical inertia that is a little bit moved slowly. But for the renewable generation systems, that can be very faster response. So in that way, then in the current systems, I would say that the penetration of renewable will affect, of course, the restoration capability of the system. But the other thing is, this is because of the current grid structure that we have a mixture between the conventional generation and the renewable generation. But if we look at that more and more renewable generation put into the grid in the system, probably the requirement can be different. And in that sense, if we look back to the blackout in Sri Lanka, then that was because then they are not allowed to do the restoration or to do some sort of generation. So in the future, probably this can be changed because we have a much higher penetration of renewable energy systems. Yes, I would say then that this will definitely affect the operation and also in terms of handling critical events in the power grid.
Yes, totally. So yeah, so I would also like to seek Professor Mishra's opinion, as there was a recent event of 9 p.m. 9 minutes, as we know that India is well, not dominated by power electronics right now, and it is quite robust. So when it comes to because we are focusing more on a power electronic based dominated power system, how do you think it will fare up in India, where it's a huge load, and what are the measures that could be taken, or do you recommend this power electronics dominated power systems in terms of, well, let's say control and stability and other there could be other things, which is a necessity right now because we have to come up with more power electronics, but in terms of, let's say, the reliability of operation and everything. So how does it fare up in a with a big load like that?
Thank you, Shubham. See, basically, if you see the Indian condition now, the most important scenario could be considering different microgrids, and those microgrid may be connected in a microgrid cluster, and that cluster can be connected to the distribution system, and finally the distribution system can lead to the transmission and above. This is because if you make the things smaller and smaller, even if there is a unstable operation, as you were mentioning, the blackout or the isolation will be very easy, and that islanded operation can be handled easily as compared to a very large grid scenario. But the large grid scenario has its own advantage when it is looking from the perspective of rotating machine based system. So when we have rotating machine system, we migrate towards larger and larger grid because they will help each other. But when you are looking for a renewable based scenario where more power electronic things comes into picture, we must go as small as possible. So the microgrid will lead the scenario. And that is also a blessing in disguise for the Indian condition, because now anyway, we will do the infrastructure establishment, unlike the developed country where infrastructure is already existing. Now, since anyway we are going to do the infrastructure in the distribution level, maybe if we go for a microgrid cluster sort of thing at distribution level, it will help us in making the grid more greener and renewable based. Because anyway, we are going to invest in the infrastructure. So there is a distinct difference between the scenario in the Western countries and maybe in the Indian subcontinent, where we are now preparing for the infrastructure investment vis-a-vis in other subcontinent or continent. It is already developed scenario. Now coming to the whole renewable or power electronic based scenario, it will be always better if we go for a data driven control rather than just going for a master slave operation mode of control. The data driven control will be always going for a supervisory sort of thing, and it will adopt many of its control parameter as well as protection parameter to make the power electronic based microgrid more stable, then more reliable, and more 24/7 operative.
Yes. Thank you, Professor Mishra. So I will not take much time, as I know that it is very late everywhere. So I will just have a final question. And Rui, if you have any question, you can also join in and ask, as you have a industry perspective over this theme. So you can always join and ask. But I will just end up with a final question. So when you talked about developed countries, I think that can also go wrong, because a few days ago I was reading more about the recent blackout in California, where they initially blamed the renewable energy sources to be the main culprit. But later on, I think it was some, the temperature rise, which was affecting the gas-based power stations, and that caused the blackout. But anyway, I think the operators, they are actually not very happy with all the investment that they have made in renewable energy sources, because they are anyway importing power from the neighboring states or the neighboring cities. So the profit margin is not good, or in fact they are in huge loss. So they are actually saying that they should have invested more in maybe, or invested this money in nuclear energy. So how does the planning come into play when you are targeting to increase the generation from renewable energy sources, both in Indian context and also in Denmark? If Yongheng, you can take that into account.
So you are asking to me probably?
Yes, Professor Mishra, you can probably talk about
So
India, and Yongheng can.
Yes. So as you told rightly, again, it is a local phenomenon, and the renewable energy what I was mentioning and the infrastructure what I was mentioning is basically the infrastructure that we are going to do today, whether we should go for a conventional distribution line based approach or we should go for a microgrid approach. We have both the two with our option available. But at many places, this option may not be available because they have already a robust distribution network. Now coming to the example that you gave, what type of source and the cleaner source is accepted by the society is the most important one. Now, for example, as you told, nuclear energy. If the nuclear energy is not accepted by the society, whatever you say, the people will not accept it. Similarly, if I say that hydrogen-based thing, if there is a fear in the mind of the people that it should not be accepted as a source, that will never see the light of the country or the society. So, based on the level your societal behavior remains, we have to take the sources accordingly and educate the people for that specific type of cleaner and greener operation, so that they can integrate that to their day-to-day life. So in the Indian context, therefore, the photovoltaic one will be more beneficial as well as more acceptable to the society, because it can be integrated starting from 400 volt or even 230 volt single phase to the 400 kV level. Maybe this scenario may not be available in many countries as well. So in the Indian context, if I summarize, the photovoltaic system will be definitely more accepted, and the public at a large can also be involved in this photovoltaic as a source acceptance by investing good amount of money from their own pocket.
Yes, yes, I agree. So, Yongeng, would you like to add that some notes on the European context? What would be?
Yes, I agree with Professor Mishra regarding the aspects and how to increase the social society acceptance of renewable energies, in particular PV systems in India. But also, this is one of the things then in Europe, then how to increase the common sense of adopting renewable energies in a way to tackle the environmental challenges. And but of course, the development or the acceptance of using renewable energy, one thing is that we put more efforts into the education. This is one of the way. And but of course, the other thing is, I would say, this heavily relied on the technology development and also government policies, and how we can further reduce the cost, then convincing the people in Europe to accept this technology. And this is something that we as engineers to focus on to improve this view on renewable energy systems. But in conclusion, and I would say that this is something that we are still putting on a lot of efforts in, and but we would expect more technology developments in a way that this will be widely accepted by the people in Europe and also beyond in the entire world. Yeah.
Yes, thank you, Yongeng. So we do not have to extend this much, because there will always be discussion and there will also always be insights on improvement further in promoting or having renewable energy sources in the grid. So I would like to end this.
I think there are two questions. Maybe we can quickly.
Yes, I will do that. Yes.
Yeah.
So there are two questions before we end the final session. So one of them is, what are the challenges for integrating solar energy in electrical grid for the African countries or African continent? So yeah.
Maybe I can comment a little bit on this one, because
Yes.
last year we run IEEE, not we, IEEE Power Electronics Society had this Empower a Billion Lives competition. So basically, the way there is we wanted to find some solutions to help the African countries and regions to increase the integration of solar energy. And I would say that the power infrastructure in most of the African countries, it's not that advanced, or how to say that we need a lot of investments to improve the power grid infrastructure. So if we consider this one, And the most important thing to integrate solar energy in the electric grid in Africa, then I would say that's how we can develop low-cost solar PV systems through like technologies, topologies or other ways, business models. But the other thing is the most effective way to do so, to integrate solar energy in African countries, that will be standalone system, and then this will be the most efficient way, and we avoid upgrading the power grid infrastructure.
Perfect. Yeah.
Yeah, I agree with Yonghang, but I will just add 1-2 points here.
Yes.
This is more analogous to Indian context also. Now, if you read the news, even Tata has gone for a company called Tata Microgrid, who is going to establish 200 microgrids in the Indian subcontinent. So same type of thing, the microgrid are isolated, no doubt, but each microgrid can also be connected to another microgrid if infrastructure permits in the future. So that way, the overall system will be integrated, and the African country is no in any way much different than many of our rural Indian infrastructure also. So the microgrid cluster may be a good solution for making African country 100% renewable energy based in the long run.
Yes. Yes. Totally. So yes. So we will move on to the next question, and it is in fact from Rui. Do you foresee emerging techniques that can further lower the cost of solar energy production? So yes, this is what Yongheng is already doing, or he has already done. This is the levelized cost of energy based on reliability. So evaluation of powertronic converters, which is also reducing the cost of energy or energy production, or even lowering the cost of maintenance as well. So Yongheng, you can speak a bit, and then we will hand it over to Professor Mishra.
Yeah, I think as you also pointed out, one of the ways is we trying to improve the reliability or the service time of the power converters we have installed on site in a way that this is something that we can lower the cost of energy. But the other thing is we also engineers are also looking ways to do this one from the material perspective, and how we can further lower the cost of manufacturing solar PV cells and also other components when we want to integrate solar energy into the grid. But for us, because and also because my background is on power electronics and also control of PV systems, the ways to do so is to improve the efficiency and the reliability of power electronics converters. That's one of the ways to lower the cost of solar PV energy.
Yes, yes. So this is what we have been doing here, and then I will put this note to Professor Mishra about his comments on this question.
Yeah, thank you, Shubham. Actually, when we talk about the cost of solar power or solar energy production, this cost is something a very, very economical, or a term that is coming from the economics. See, when you go for any solar installation, it has a capital cost. This capital cost comes from borrowing from a bank or maybe some investor. So there will be some interest component included in it. There will maybe some government subsidy to it. Then there may be some operational cost. Then this operational cost increases or decreases based on the manpower that you are getting. And similarly, the the overall cost comes from the overall life cycle of the system. So if you see this way, I will go for the cost of the solar production. Maybe I will divide it into three parts. One is the capital expenditure. Another is the operation and maintenance. And third is the societal acceptance and its business perspective. Overall, if you add all the three, then only you will be able to forecast or go for a bidding of cost of solar energy production. Now, based on the country, these three parts will go on changing. The material portion will only little bit change to the initial investment here and there. The operation cost, where human beings are involved and where automation is involved, will make a lot of difference. And third, when I am talking about human being, that is human force, it depends on the country and their wage system. And last but not the least, whatever energy producing, I am getting a production. If suppose I get a guaranteed income out of it, then I will go for a very, very cheap power production as compared to a non-guaranteed energy production mode. So the government regulation and the tariff structure will play also a very vital role in the cost of solar energy production calculation and its sustainability.
Yes, I think that is very well said by Professor Mishra and Yongheng to have their perspectives on the cost of solar energy production from material level to the final energy extraction level. And this will obviously vary for countries which are still in the developing stage and which are developed. So that gives an overall brief about what are the the emerging techniques that can be used at different levels. So yes, thank you so much. And this is very budding for young researchers like us to take up these kind of research challenges and work further in the future. So that was all the Congress is all about, to take these challenges and work in the future. So I hope that this has helped a lot of young professionals out there in the world. So with this, I will hand the session to VZ again.
Okay, thanks.
Thank you.
Yes. Yeah.
Yep.
So thank you very much. So I think we are still okay, right? So because we run a bit late. So thanks again for our speaker, Sukumar, and thanks for all the panel members here, Subham and Ray and Yongheng. So I think the discussion is very impressive, and it actually is really good, and it's a good discussion, right, on the renewable energy resources here. So okay, so due to the time, I think we can call it a day, right? So
or rather call it a night for us.
Yes, of course. Yeah. So yeah, thank you again, and thanks for all the participants, right, for your patience and the attendance. So you can hopefully can follow all the LinkedIn webpage for our future events, or also our actually our website. So thank you very much, and thank you for all. And
thank you, Gerard, as well, for joining in so late from Sweden.
Yes. Yeah, really thanks, Sukumar, because we know it's very late in India. So
yes,
thank you all. Yes.
Thank you all. Thank you all.
Thank you.
Thank you. Thank you all.
It was very nice. Yeah.
Okay.
Yeah.
Yeah.
Good night.
Okay, good night.
Okay.
Yes.
Okay. Good night.
Yeah.
Bye bye.
See you.